Okay, welcome everyone. Today and tomorrow, Vasu and Hunter will tell us a fascinating story about quasi-symmetric divided differences. First part made by Vasu of the combinatorial set algebra.
Thank you. Thank you to June and Matt for inviting me, us rather. So I'm going to talk about quasi-symmetric divided differences in forest polynomials. This is joint work with Philippe Nadeau and Hunter Spink. So my aim is to sort of give you hopefully general intro to the combinatorial side of the story, introduce the main protagonists, which are meant to evoke the Schubert story in case you're familiar with it, and any and all geometric underpinnings and nitty-gritties are for tomorrow. So let me lay the groundwork for the story tomorrow, and of course I'm happy to have questions. Okay. So my main motivation of dating back to 2018 was understanding a symmetrization procedure which I came across in Postnikov's work. So let me put that procedure on the board and describe the various things it encodes. So this is divided symmetrization, and what it does is it takes, let's say, a polynomial with rational coefficients and produces a symmetric polynomial via the following procedure. So f is going to get symmetrized, so we should expect a symmetric group acting on this guy. So here's f in the numerator, and since the term divided appears here, so you should expect some rational function aspect. So this is the denominator, I going from 1 to n. And sigma. So this procedure, you take a polynomial, you run it through this machine, out pops a symmetric polynomial. Okay, so despite appearances, this is a symmetric polynomial. It's not worth looking at this procedure if the degree of f is too small, because you're dividing by something of degree n-1. So the first time it becomes interesting is degree n-1, and then beyond. Okay. All right, so I'm claiming it's interesting. You should believe me. So let me give you some idea for why this might be interesting to you. So here's a families of polynomials, and let me call this guy. Let me use shorthand for divided symmetrization. Okay, so here's f, and I'll just record what this quantity encodes. If you feed this machine the polynomial x1 to the c1, x1 plus x2 to the c2, all the way through x1 plus xn minus 1 to the cn minus 1, where the c's add up to cn minus 1. So this is a homogeneous polynomial of degree n-1. What does this guy encode? It encodes these this fascinating family of numbers called mixed Eulerian numbers. And these are mixed volumes of hypersimplices where the C sub i's counts the number of copies of the ith hypersimplex. Okay, so these are mixed volumes. Okay, so mixed volumes of hypersimplices. So that's one case. Let me take one more case, which is I feed this guy Schubert polynomials of degree n-1, and I get a number again. So Schubert polynomial, you would not need the formal definition or the combinatorial definition ever in this story. So let me not try and define it here. So this guy represents the class of a Schubert variety and the convolution ring of the complete flag variety. So if I take one of these guys with length, the Schubert polynomial where W has n-1 as the number of inversions, then this is a coefficient. So this guy is the coefficient of, say, this class inside the class of the permutahedral toric variety, in the class of, let's say, permutahedral toric variety. So both of these might be things you may have come across in different contexts, maybe discrete geometry or Schubert calculus. Okay. Let me add in a third thing here. because why not? So if you had a monomial, and this time I will not care about the degree constraint. If you had a monomial where the lambdas were strictly or weakly decreasing, let me pick them to be non-negative integers, then this divided symmetrization is the lattice point enumerator. This guy is the lattice point enumerator for the trimmed permutahedron. Okay. So there's a Minkowski difference that you can take. And then you count the lattice points inside this guy. Each lattice point gets assigned a monomial, and you get this symmetric polynomial for this seed f. Okay, so Schubert calculus, some discrete geometry, and well, same. Okay. So this is the side of the story which I'm particularly interested in. This second row. This one, let me assign some names here. So this is Postnikov 05. This I got here through work of Dave Anderson and Juliana Timachko. So let me assign this computation as a special case of some results in this paper, which are for regular semi-simple Hessenberg varieties. Okay, so the permutahedral variety is one case of a particular Hessenberg function. And here, let me just say this is Brion. Maybe 88. Okay, so potentially, this is the side of the story some of you folks are more interested in or understand better. My concern was on the left-hand side. You could say that, well, the left-hand side is just polynomials. There's a little bit more to the left-hand side. Everything I've shown so far is a Schubert positive input. Okay, so there's positivity. In this case, these are positive numbers. These are non-negative integers. This is living inside symmetric polynomials with non-negative integer coefficients. So those are positivities on the right-hand side. I want you to observe that the left-hand side is all Schubert positive. Okay, so all inputs, so note, all our inputs are Schubert positive. All our inputs, input F, are Schubert. So I want to use this as motivation to sort of argue for why, well, this is an algebraic procedure. How do you do this combinatorially? It suffices in some sense to fixate on Schubert positivity as something that's inherent in the input, and then trying to turn this into a combinatorial procedure. So the question I'm trying to answer is, how does one combinatorially compute? So question, how does one combinatorially, with emphasis on combinatorially, how does one combinatorially compute the divided subdivision? Yes.
What's the reason for dividing by that polynomial as opposed to any other?
So if you come, so on the one hand, this computes the degree on the permutahedral toric variety. So if you were to just start there, this is an expression that pops out just by force. What I started from involved Dave's result with Juliana was the class of this particular Hessenberg is given by a Vandermonde determinant-like expression. Where the differences that you see, that the ones that are missing are precisely the guys that show up in the denominator. So if you started here and you're like, okay, I want this expanded in terms of Schubert polynomials, just anti-symmetrization, the way you compute Schubert coefficients, by hitting some maximal anti-symmetrizer and extracting a coefficient, would naturally lead you to this symmetrization expression as well. Okay, so at least two reasons to get to here. We start with this expression. Other questions? Okay, so all right. So let me give you two answers to this. One not very satisfactory, and the other one hopefully quite satisfactory. So the first one involves quasisymmetric polynomials. Let me introduce them in lemma/definition style. So here's a definition of what it means to be quasisymmetric. So if you hand me a polynomial, I'll define an operator, which is essentially to Bergeron and Sotile from their work in '98, to define R sub I to be this following new polynomial, which has the first I minus 1 x's in the same way that were present in the original guy. Xi is set to 0, and the remaining variables are then reindexed.
You have reindex.
Yeah, right. So I wasn't true to my word. Indeed, reindex. Okay, so Xi onwards. So if you're working with a finite set of variables, applications of Ri are going to lose variables. Okay, so if you had n variables to begin with, you apply some Ri, probably lose variables. You apply successes of several such Ris, you well, might end up with 0. So this is an operator that was introduced in a geometric context by Nantel Bergeron and Frank Sotile. So I want to use this operator to define what it means for a polynomial to be quasisymmetric. So I say f is quasisymmetric if something holds, and what is that something? Xn if Ri of f equals Ri plus 1 of x. All 1. Applying this map R sub I produces the same result as applying the map R sub I plus 1. This detects some sort of shift in variance. Okay, so if you want to informally keep something in mind, this equality is detecting the sort of shift in variance that is traditionally used to define quasisymmetry. Okay, so this here. So in particular, I want us to observe that symmetric polynomials are certainly quasisymmetric. Okay, so this is a family that contains things we might care about. Any questions? Okay, so here's the algebraic object whose geometry Hunter shall talk about tomorrow. Define this QSIM n, this is the quasisymmetric coinvariance, as the polynomial quotient. So this is going to be polynomials in n variables, and then I quotient out by this here. Oh, so these are, my apologies, I should have written. So this equality is this equality where QSIM n plus is the ideal generated by a positive degree plus zero. Okay. So this guy was studied by Jean-Christophe Aval and the Bergeron brothers. So this was in 2004, and their motivation was simply the fact that if this Q was missing, then this is a fairly interesting quotient. Right? This is the homology ring of the complete Phi variety. It has dimension n factorial. A lot of my mathematical career is built out of understanding the case without the Q. So they're like, okay, how about throwing a Q here and see what happens? And I guess the sales pitch here is interesting things happen. Okay, and well, the first interesting thing, if you're a combinatorialist, as a vector space, you can ask for its dimension, and this dimension is a Catalan number. Okay, so the result that was proven by this trio is this is the nth Kaplan number. And they produced a monomial basis indexed by Dick Potts. Okay, so they gave you monomial basis, ABV produced a monomial basis for this quotient indexed by Dick Potts. And I'm just going to call it the ABB basis. The specifics, again, are unimportant. So let's just work with this. And if you have questions, of course, I'm happy to say more later.
Structure constants non-negative for the multiplication.
In the monomial case?
Yeah.
No. So no, so not going to be able to multiply these guys and then expand it. Monomial basis, I think. Let me return to that later because I'll produce a better basis and then the positivity will be proven. So these guys produce a monomial basis that realizes that that dimension, that number as the dimension. And I sort of want to say, if you think about matroids, that the Hilbert series for this quotient is a specialization of the Tuck polynomial of the Catalan matroid. Okay, so if you know your lattice path matroids, the Hilbert series is the Tuck polynomial of the Catalan matroid. Where one of the variables is set to 1. Okay, so x equals 1, q equals 1, and retain the other one. Okay. Specialization, a specialization set. So it's not palindromic. So if you're trying to think of like what geometry you could attach to this object, you'll need to do some work here, right? So it's not going to be, it's probably interesting and not so trivial. Okay, so let me say the first theorem, which allows you to compute this. I think this has to go because the rest has to remain. So theorem, one way to compute this, one way to perform this computation is the following. So for f, homogeneous of degree n-1, so I'm going to pick something that has the right degree, homogeneous of degree n-1. Take its representative, modulo this ideal, and have this expansion in this particular basis. Okay, so take a distinguished choice of representative in the ABB basis. So let f bar be the representation, be the representative in the ABB basis. Then the following happens. So then divided symmetrization is taking the sum of coefficients in the ABB basis. Okay, so if you could perform this task of reducing polynomials, modulo this ideal, and going towards that particular monomial basis, looking for an expansion in that basis, then this task is easy. You end up evaluating, setting all the xi's equal to 1. Okay. Well, then you're saying, well, you've just shoved the difficulty of this task into the task of how does one reduce modulo this ideal. Okay, so that's one theorem, and I want to present something that looks slightly different, and then the rest of the talk is going to be trying to relate the two statements. Okay, any questions at this stage?
Mm-hmm. Sorry, to make sure I understand. So F bar is like a linear combination of
ABB monomials, yes.
Okay.
So this guy has top degree n-1. Okay, so the largest degree that you see in this quotient is n-1. So if you start here, you get an expansion coming from these ABB monomials of degree n-1. I just look at that and I set all xi's equal to 1. And that is the answer of performing the symmetrization procedure. Okay, so somehow the ideal of quasi-symmetric polynomials knows something about the symmetrization procedure.
If you raise a degree, what happens?
Oh, great question. I can give you an answer. The answer is that I can compute Schubert of any degree. It's always non-negative and monomial positive. I don't understand its meaning geometrically. If that's what you're asking, I have no idea. In the dominant case, it's a lattice point count. That guy is a Schubert polynomial of arbitrary degree. So if you replace this with any Schubert polynomial, you still get expansions in here. But I don't know of a geometric interpretation for those things. Actually, that was a question that Alejandro asked me in 2018 or so.
As far as the smallest polynomial, right?
F bar, yes, it is.
And you plug in always,
Correct.
you got a number.
Correct. It isn't. I mean, this is degree n minus one, degree n minus one. This thing is in the ground field. Yeah. So when I said that the smallest degree that is actually interesting is when things are of degree n minus one, because you get numbers. Because these are intersection numbers in the permutahedral toric variety case, right?
So F and F bar differ by the element in that's the main cubes.
Correct.
Okay.
Yes. I mean, there's several representatives. I'm picking a distinguishable. Other questions? Okay. All right. So let me present a second take on this computation. And this is where I get to define the object in the title, quasisymmetric divider. So here's version 2. So now define, so this is my quasisymmetric divider difference. Differences. What is this operation? It's going to involve some division as divider differences should. And what I'm going to do is take the differences, bring this guy to the left, or this one to the right, rather. And then you know that there's some redundant information in that difference. You can divide by xi. And you get a map that goes from polynomials to polynomials. Okay, so this is my definition of a quasisymmetric divided difference operator. Okay. And you can actually realize this as a composition of ordinary divided difference. Right, so this is the BGG divided difference up here, composed with the Bergeron-Sottile RI map. So this BS 98. Okay. Okay, so I'm calling this a quasisymmetric divided difference. There better be good reason for going with this name. Let me start small. Let's say that F quasisymmetric TIF 0 for all one listing. No surprise. Symmetric polynomials are killed by divided differences. Quasisymmetric polynomials are killed by these operators. So that's step 0. Okay, so how do you use these operators to compute the same this procedure? So this is a theorem of Hunter. So this was Philippe and I. And then Hunter told us that the way to do things is use operators and polynomials. So here's the theorem. All right, so I'm going to stick with polynomials of degree n minus 1, just for convenience. So same hypothesis as before. the divided symmetrization can be computed as a bunch of quasisymmetric divided differences applied to your input. So there's no picking a representative anymore. You just straight up start with F, hit it with a bunch of quasisymmetric divided differences, keep doing this until this list keeps shrinking. And at the end, you've done, so each of these t's drops in degree. So degree n-1. At the end of this procedure, you get a constant, and that's the number that you can realize differently in this map. I want us to observe.
That's not true if F is not homogeneous. If F does not have degree n-1.
So these operators need a minor change in difference. So what you do is, maybe I can define this. Is that thing still here? Okay. So T sub I was obtained by this R sub I maps. They plugged in 0. What I do is instead put xn in those positions and then recurse. So instead of plugging in zeros, take the last variable and shove it into locations, and then the new list has treat and forget that xn was the last variable, treat xn-1 as the last variable, move into this various positions, and then recurse, and then you actually get a polynomial at the end. So the same factorization with a deformed version of quasisymmetric divided difference would compute higher degree divided symmetrization. Okay. Other questions?
Your definition of Ti with the F, so I guess the F is.
My definition of Ti is missing the F's. Thank you. Sorry, this is not equal to on the nose as well, but hopefully you'll forgive me. It's been preserved for posterity anyway, so. Okay, well, I want us to observe one more thing here, which will matter either today or tomorrow. There's n-1 factorial of these compositions of T in this product. Okay, so there's n-1 factorial summands, and each of those is acting on F and pulling out a number. Those numbers are getting assembled to give you a coefficient. If F was a Schubert polynomial, that's computing a coefficient of a Schubert class corresponding to that permutation as a sum of n-1 factorial numbers. Okay. All right, let me return to this at the very end. Okay, so if you're staring at these two statements, you probably have to wonder, well, what does this reduction modulo QSIM know about, or how does it interact with, how does it play with these quasisymmetric divided differences? So statements of different flavors, and you could ask, well, is there a basis of the polynomial ring that plays the role that Schubert polynomials play in the classical story? Okay, so let me change. So this question, is there a quasisymmetric divided difference friendly basis for the polynomial ring? Okay, so that's what I'm aiming for next. Okay, so this is going to be some new combinatorics. So let me introduce the object, and I'm going to hope that examples shall have to suffice. Okay, so I could define them formally, and we'd miss out on some sun. So let me not keep you for longer than one is intended to be the case. So examples shall have to do. So my object, instead of permutations, is going to be a collection of trees. So let me stick to my notes so that I can do some computation after. Okay. So index forest, what is this guy? I start with the integer lattice. I only care about the positive ones for the moment. If you want to do backstable stuff, be my guest. So there's going to be the Z, the non-negative positive part of Z right here. And on top of this guy, I'm gonna plant some trees, root pointing up. Okay, so here's trees on this guy. Internal node, these leaves are going to be coming from this copy of the positive integers, and there's going to be trees. Trees will always be supported on intervals. So there can be a collection of trees. Let me take another one. So maybe this guy, this guy, this guy. This object, collections of trees, is what I call an indexed forest.
Binary trees.
Binary tree. Thank you. So I'll just put that there. Rooted material, binary trees, disjoint support, supported on intervals, and all support disjoint. All right. On this object, I will define a move which is combinatorially meant to mimic the fact that when you take a permutation, multiply it by the simple transposition Si, you get something interesting happening if and only if the length drops. You lose an inversion. Okay? So for me, I'll define an operation that is meant to lose internal nodes. Okay? So there's the obvious, well, if you do this, there's not much choices. You could either start at the root or at the leaf, take things away, and still get indexed forest. Turns out the choice of removing the root node is not the good one. You really want to start removing leaves. So let me tell you some things that you can, in fact, remove. Such a thing, let me call it a wedge, because it looks like one. So this node, which sees two leaves, is something I can get away, remove. This other choice right here, this is a wedge that I can get rid of. And then this, there are three choices. This is playing the role of descents in the usual permutation story, if you know it.
You missed one wedge.
All right, okay. No. Okay, so now that we have that correct, you know what this is. It's a wedge, and it's seeing two leaves. And what I can do is a trimming operation as follows. Okay, so trimming operation, so one can trim a forest, an indexed forest. And what does this trim do? I specify the wedge by its left, by the label of the left leaf. Okay, so I can trim the 9, that will be this wedge, the 7, that'll be that wedge, and the 2. Okay, so 2, 7, and 9 are my trimmable positions. So let me encode that. Our positions one can trim at, positions one can trim at. And what does the trim do? Well, it squishes this wedge so that it becomes a point. So you want to get rid of a node, just imagine that this thing becomes a point and joins. So let me do, so this is a move, let's say F, and I'm going to trim in the 7th position. So F going to F divided by 7. So this becomes a leaf. So let's redraw this, and hopefully I don't mess this up. So this guy, no change, right? This is the same as before. And this guy will now become a tree on 3 internal nodes, and it's going to go from 6 through 9. Okay, so 1, 2, 3. Record the labels. So 6 through 9 become this. So when you squish this to a leaf, the 7 survives, and you reindex the remaining numbers to sort of always be the positive natural numbers at all times. Okay, so there's no holes that are being created when you turn this wedge into a loop. You could have done T2, a trim at this position, and this would have become a single node sitting right here, and the remaining guys would get shifted. Okay, so you realize something, you can repeat these trims, and the forest loses internal nodes one at a time until it becomes the empty forest. If you're thinking this in terms of reduced words, you're multiplying by simple transpositions on the right-hand side, always losing a descent, and eventually you hit the identity permutation. Okay. So this act is the act of trimming, multiplying by S sub I. Okay. Right, let's see, let me use this word. So if you're seeing that statement in color on the board on the far right, I want to write the parallel statement and not tell you how to define this polynomial family. So forest polynomials are the unique family of homogeneous polynomials with the following property. Okay, so it's a theorem. So there's a unique family of homogeneous polynomials with the following property. Homogeneous polynomials. And this is going to be indexed by indexed forests, okay, collections of binary trees, such as that. And what are the defining features of this family? Well, the usual one, the empty index forest is 1. And for any higher degree index forest, I can trim at a legal position and get a new forest polynomial or 0. Right? So T sub I applied to a forest polynomial produces either a new forest polynomial or 0, depending on if the move that I was trying to do was legal or not. In here, had you done like a T6, well, 6 is not a wedge, so that forest polynomial would have been sent to 0. Okay, so this is if I is trimmable and otherwise. Yes.
So one can trim it only at wedge, like.
Yes. So you can only eat this thing starting at the leaves, going up. So you start seeing linear extensions come into play organically. And you're starting at the leaf, eat up a forest. So the number of reduced words are now going to be linear extensions. Other questions?
Factory if roots are below.
Yes. Like you, other than just a good cosmetic change.
I don't know. Is there a reason?
The reason could be that I studied computer science as an undergrad. No. I don't know. I just went with it and never questioned, never doubted myself, if I would say so.
This matches the usual convention for drawing divided differences as braids. Have as a heap, you would put the ground down here. And you would draw a bunch of X's that stack on top of each other to represent the operation.
Yeah, so this procedure, thank you, Andrew, is actually like, you're doing maps, polynomial compositions of or procedure variables where one guy becomes 0 and then you lose a variable. This act of losing a variable is sort of captured by two variables, adjacent variables becoming a new single variable, and this thing propagating upward. But yeah. Other questions? Okay, all right. So here's a nice family of polynomials. It's actually quite combinatorial. I'm just trying to do as little of, since I never handed you a Schubert polynomial, I feel duty bound to not really hand you a positive monomial expansion for this family as well. Okay, it'd be disrespectful to Schubert polynomials. Okay, so what do I want to say? Well, here's the relation to, so two facts that let me just mention. You actually do get a basis for the polynomial ring using these forest polynomials. Okay, so these guys do form a basis. F. And let me just say that if your trimmable nodes are always contained or a subset of n, then this collection spans the polynomial ring in x1 through xn. As a basis, Morgan spans. It's a basis for the polynomial. Of course, you can work with Z coefficients. Okay. And why is this a good basis for working modulo Q-sim? Well, it turns out that when you try and reduce a forest polynomial modulo quasi-symmetric polynomials, you either get 0 or you don't need to reduce the forest polynomial at all. It's already expressed in the ABB basis. Okay, so here's something that happens in Schubert land. If you work with Lasker-Schutz-Berger-Schubert polynomials, they are combinations of Artin monomials. And if you take a Schubert polynomial and try and reduce modulo the ideal of symmetric polynomials, it's either 0 or needs no reduction. Same thing happens in this case as well. Okay, so let me write that fact, and that sort of connects the two theorems, one of which I have clearly raised. Okay, so theorem, Schubert polynomial, forest polynomial, modulo Q-sim is either the forest polynomial itself, if the support is, if it's completely supported on the first n numbers. Okay, so this guy is supported on 10, but it's not supported on the first 9, clearly. Okay, so this forest polynomial, if you try, it uses only variables x1 through x9. If you try to reduce this modulo Q-sim 9, it would be 0. So this one is 0 or no reduction needed. What is this saying? It's saying that this is already expressed in the ABB basis, already in the In other words, the all ones evaluation of this guy is easy, right? You just compute the sum of coefficients. It's actually the number of linear extensions of a tree. So it has a hook length formula. Okay, so it's a very precise quantity that you get when you perform divided symmetrizations of this guy. You either get zeros or you get the number of linear extensions of the associated tree. Yeah.
Are the coefficients of the forest polynomials, since you didn't tell us what they are they actually rational?
They are positive, non-negative integral.
So which of the expansions need the Q coefficient?
Nothing does. So I said you could have worked from the very beginning with Z, and nothing would change. So you think you'd be happier if I just wrote a Z here? I could do that.
No, I mean, I was thinking maybe you had a reason for it.
No, I'm sorry. I should have perhaps. When I was writing my notes, I kept shifting between Q and Z on occasions. I said, okay, let me not try and mess things around. I'm sticking with Q just for convenience. This is everything with integers. There's no actual rational numbers involved in this story the way I've told it at any point.
Whenever you have like a positive expansion, the coefficients are actually the coefficient.
I can, yes. Let me just write down a forest polynomial. I'll not tell you where it comes from. If you ask me at 3, I shall. But let me not. Okay, so here's a very small example, but it will allow me to state a theorem which sort of mimics or tells you what the analog of these nil-Coxeter relations are. Okay, and that shall matter. Okay, so here's a very small example. So here's a forest polynomial supported on 1, 2, 3, 4. Here's a forest supported on 1, 2, 3, 4. Believe me when I say when the forest polynomial is x1 squared x2 plus x1 squared x3. I can trim it in 2 ways. I can squish this guy or this guy. So this is f by 3, And this will be a new forest polynomial. Where this guy is now a left comb supported on 1, 2, 3. And this guy is x1 squared. Okay. So you can actually verify this if you remember the definition. You could have trimmed this guy, and then you'd have a comb pointing to the right. This is again 1, 2, 3, and this is f trim 1, and this one is x1, x2. Keep going. Well, in this case, you can trim this again and trim this again, and you will get a single tree supported at 1, 2, which you can trim further and get the. Okay. So if you did, so now this guy can be done f sub 2, 3, followed by f sub f divided by 1 again. Same result. This one is in x1, and this one is. Okay, so this is what you start with some guy, you apply trims in all possible ways, and you can trim it down to. And this is exactly witnessing this particular property.
All of these are also Schubert polynomials.
Yeah, not always the case.
But do you know which forest polynomials are Schubert polynomials?
Are on the nose Schubert polynomials.
I mean, like this one is.
Yeah, this one is. I think it will most likely never happen. So let me say this: Schubert's to forests is a general case of Schur's into fundamentals, and it's literally never the case that a Schur is a fundamental ever. Okay, so yeah, so this story, the Schubert to forest transition matrix it contains the Schur to fundamental. So this is a lift of the Schur to fundamental story, and in this case, you sort of don't expect coincidences unless you're in very low degrees. And of course, if your forest has a single wedge, it is Schubert's subtransposition. So x1, x1 plus x2, x1 plus x2. So that certainly works. And odds are you'll not see much of that. You'll always get the elementaries and the homogeneous symmetric functions. Okay, because those are fundamentals. But it probably won't function for much longer than that. Okay. Okay, so well, you see a relation here that doing this move resulted in the same tree as this move. And you're like, okay, are there any other relations? In fact, there are no other relations. So the analog of this nil-Coxeter relation is the Thompson monoid. So theorem, these trimming operations carry a representation of the positive Thompson monoid. So the T sub I satisfy the quasi-symmetric divided differences, satisfy the defining relations of the Thompson monoid, satisfy the relations of the positive Thompson. At some point when I learned this, I thought my world was going to change, but not much happens outside of, like this comes from the theory of amenable groups and so on and so forth, Thompson's group F, in fact. But yeah, so the ITJ, Tj, T sub I plus 1. So if I exceeds J, you can do this simple computation.
Plus 1 exceeds J?
No, so if I was to look at this guy, I'm doing a T3, T1. So this is representing a T3, T1. Right, T1. And this is saying a T2, T1, the opposite order, right? So this one's, and they are the same. So the shift in indices is it's actually a commutation, but if you work with the definition which involves shifting indices, this one's, not asymptotes.
The statement is that there are no other relations.
Correct. So if you gave me a string of T's and you're like, what are? So this is all it is saying is, if you hand me a forest, there's linear extension many ways to eat it so that it becomes the empty forest. These relations are simply telling you, if you had wedge, you could eat this wedge first and this wedge next, or the other order. So this could be 1, 2, 3, 4. You finish this first and this next. That's that. or you finish this first, this guy gets shifted, then you finish this next, and that's this relation. And there are no other relations.
Can we state it in some other way so that it's clear that your intention was, and there are two satisfied.
Just say, and there are no other relations.
This is not.
I was going to start rewriting with representation of, okay, and
These generate.
these generate, and these generate, these generate. Is that any better?
Leave one satisfied.
There's two sides.
Oh, yes, it's actually brutal today.
You started it.
Okay.
Thanks, sir.
All right, super. Other thoughts before I use my last 10 minutes and hopefully not make any typos. Okay, let's see. Okay, so here's a statement that I wrote, which allows you to answer the question, well, how does one expand a polynomial in terms of Schubert polynomials? The story says, apply divided differences to your polynomial and then extract the constant term. And that will allow you to expand any polynomial in terms of Schubert polynomials. So question, well, how does one do this for forest polynomials? So you just need the analog of the trimming sequence or reduced wood. So for every forest, I can write down a trimming sequence, and the trimming sequence encodes how that forest gets eaten away at the leaves and become the empty forest. Okay? So trimming sequences are my analog for reduced words of a permutation. Okay? So these guys are analogs for reduced. So what is a trimming sequence? Well, you start F, you maybe trim at some juncture I1, then you trim at some juncture in this new forest at I2, and so on. And finally, you get the empty index forest, then you can read off this sequence in opposite order. So this implies that IK down to I1 is a trimming sequence for and the Thomson-Monod relations tell you that two trimming sequences for the same forest are actually the same as operators. Okay, so those relations tell you that you could have trimmed the forest differently. You will actually get a well-defined operator T sub F to be T sub IK, T sub IK minus 1, I1. This operator is independent of the choice of the trimming sequence. It's independent of the choice. Okay, so this is the analog for del sub W, independent of the choice of reduced wood. Okay, so you see where this is going. I told you that the forest polynomials are a basis. I've handed you a well-defined operator, which depends on a trimming sequence. And you're like, okay, let's just apply this to a polynomial, extract constant term, and that should be the re-expression. And that is indeed the case. Any polynomial f. So any f, any polynomial f expands as F0 is the constant term. So I apply a bunch of quasisymmetric divided differences for any chosen forest whose coefficient I'm looking for to my polynomial f and multiply this. Okay. So that expands. So this here is constant term. Okay. This tells you how to expand anything in terms of forest polynomials. Forest polynomials have an easy divided symmetrization. So now you can expand, compute the divided symmetrization of any polynomial going via the forest expansion.
I'm really sorry. So any polynomial small f and the assumption would be that.
Okay, I have 5 minutes. Let me say a little bit more. I want to apply this to a Schubert polynomial, right? So that was computing the divided symmetrization of Schubert polynomials was the actual goal. Let me use the 5 minutes to say something more about the decomposition of the permutahedron into n-1 factorial Bruja interval polytopes, something that shows up or showed up in Melissa and Bennett's talk at the workshop a month back. Okay, first things first, this expansion tells you that Schuberts expand positively in terms of forest polynomials. Okay, so consequence is Schuberts expand negatively, let's say, into forest polynomials. And the reason is these T trimming operations are compositions of these Bergeron-Sottile R operation and divided differences. Okay, so proof Ti is R sub I, del sub I. This acts nicely on Schuberts, produces 0 or another Schubert polynomial. This acts in a multiplicity-free manner on Schuberts. Okay, so applying this R sub I map produces a multiplicity-free combination of Schubert polynomials that is combinatorial. Okay, you can actually use K Bruja order or I minus 1 Bruja order to compute this effect. Okay, so this is actually the proof for Schubert to forest is a non-negative expansion. Okay.
This is like degenerating Schubert varieties into unions of something.
So the R sub I map in the Bergeron-Sottile context comes from trying to embed the flag variety FLN-1 into FLN using one additional vector that came from C sub n plus 1 wasn't present in Cn. And then you look at the effect on the churn roots. So you get a map from H dot of FLN plus 1 into FLN, which is exactly described by this R sub I variable substitution that I was doing earlier. Whether this is a degeneration, Hunter, is it?
I mean, he wants to know the geometric thing you're about to say.
Oh, are you okay? So if you're reading his mind, let me finish with the statement, and then I'm happy to take that question again, or Hunter can.
So it can't be happening within the flag group.
So I'm trying to see what Carl Leon's work is an answer to Jim's question, but because he degenerates, so he generates
Something else, that's the permutahedral
variety. Yeah.
So the Schubert variety, Schubert classes are extremal rays of the effective cone of the flag variety. So
It doesn't degenerate into anything inside there.
inside the flag variety, but it could be in some other context, but.
Okay, so I have exactly 1 minute. So let me state one result, and then I can take questions. So I told you that this expansion is not negative, and that it can be done combinatorially. What is not clear is that this actually computes a certain Schubert structure coefficient. So let me just finish by saying that T sub f applied to a Schubert polynomial is actually a Schubert structure coefficient, multiplication coefficient. So little Richardson coefficients coming from multiplying Schubert polynomials. There's a pair of permutations that you can attach to a forest. And this description, let me kick the can down the road because there's no time. For every trimming sequence, you can extract a pair of permutations, U and V. these two will differ by a long cycle. They differ by a Coxeter element. Okay. So applying this to a Schubert polynomial is actually computing that particular Schubert structure coefficient. Okay. And now if you go back to the expansion that I had earlier, T1 plus T2, this computing a particular class, a Schubert class inside the permutahedral toric variety, you're learning that for all these n-1 factorial summands that you're picking out, I am computing some particular toric Richardson, which differs by a particular Coxeter element, and the Schubert coefficient therein, and adding all those answers up. And this is actually the HHMP subdivision. This subdivision had shown up earlier in work of Harada, Horiguchi, Masuda, and Park. So this is a sum of n-1 factorial sequences. And each of these is computing a degree on a toric Richardson variety. So let's say I sub j is less than j. And these are all non-negative and equal to these coefficients. Okay, so let me not take any more time. I'm happy to take more questions after. So thank you.
Any questions? Is this expression for TF the shortest possible one in Simonyi?
So the length is actually going to be of the number of internal nodes. So in the
There's no reduced.
yeah, so there's no del I squared equaling 0, no analog that shrinks the length of the triple. Yes.
But the answer is
Yes. Yeah.
Can you read off the support of the forest from a trimming sequence?
Right now, maybe no, but I don't think that is hard. So just the support you said, right?
In the examples you've drawn, the forest polynomials are just the generative functions for trimming sequences, but I guess that's a coincidence. Yes, that's a coincidence.
Should be doable, but I'm not able to do it on the fly. But I think the fact that it moves fairly predictably can be captured. Like you can track the entire history with one answer. But
Okay.
Yeah.
Pipe dream-like formulas.
It depends on what you mean by pipe dream-like formulas.
Yes.
Well, he says yes. I'm like, okay, well, it depends on perspective. You can take a staircase shape, draw some tiles, and encode the weights, and the tiles will have the feature that they captured this act of merging two leaves and becoming an internal node, and you go further down the staircase, you read off a tree. So in that sense, yes, if you're working with crosses and bumps.
So it doesn't have to be.
Okay, so then the answer is yes. Okay, so there is a filling of a staircase with prescribed tiles. You can fit it to become a tree, and then you can read off the monomial weights in very much the same way as you do for a Schubert polynomial, and the sum of those fillings will give you a forest polynomial. You can do this equivariantly, and then you can actually see double Schuberts and the double version of these forests on the same model. So there's a pipe dream formula, which hopefully might show up in tomorrow's talk, which knows both Schubert polynomials, double Schuberts, and double forests, and analogs of slides, double slides, and so on and so forth.
Is there a degeneracy loci story or like some?
I no, not yet, and we haven't thought about any of this degeneracy loci or Grosvenor story. That paper is very much in flux, the second part of it. So the first one, developing the combinatorics in the equivariant setting, is done, where we have a double story for everything that I've said and pipe dream models. But if you're trying to say, is there a Knudsen-Miller version and so, and not yet.
Is the set of monomials appearing in a forest polynomial? Is the set of lattice points, all lattice points of some lattice polynomial?
So I recall checking that for a fundamental, you do not get, so if you take so fundamental quasisymmetric polynomial is the case where you have a zigzag forest. Like every node either has a child to the right or to the left. And in that case, I already remember that the thing wasn't saturated. If I took the Newton polytope of the monomials appearing, there were holes therein. So the forests are going to have,
Not saturated.
not saturated, correct. Yes.
Is there a Cauchy identity?
So when you say Cauchy identity, you want a splitting of the double Schubert xy as times Schubert in the x's times Schubert in the y's, some length after factorization. Is that?
Any sort of like these dual basis sort of statements. I mean, for
Dual basis of
like polynomials, just like combinatorial.
so I know two statements which are involved with word duality. One is the Postnikov-Stanley version of duality, which says Schubert times degree polynomials, they sum up to x of some linear form, lambda 1 x1.
Yeah, so you have that.
Yes.
Uh-huh.
Yeah, so the volume, so this Bruja interval polytope decomposition, it has n-1 factorial pieces. You can express the volume polynomial of this permutahedron, this thing as forest polynomial in the x's times skew degree polynomials in the lambda variables and add those all up. So yes, in that sense, there is a dual, some Cauchy identity. If you want double Schubert splitting into its individual constituents, I don't know is the short answer. I don't think there's a good one. I could be wrong.
And tomorrow we're going to hear the geometric meaning of these forest polynomials.
Yes, you will. Or I'm not.
I'll ask you now, but since you.
No. I think he will do the heavy lifting tomorrow. Sure. Yes.
Thank you for the very nice talk. But I have a question. So reduced words are non-trivial to compute, but linear extensions of these rooted trees are very nice. Do you have some kind of element green identity from that go to reduce words to these linear extensions from your positive expansion?
Okay, so sorry, Alejandro, I don't think I'm following the question correctly. So I'm starting on the Schubert side with the fixed. So are you asking about the Schubert to forest expansion as having some sort of?
It tells you some identity of reduced words of a permutation and maybe some.
So the paper with Philippe already contains like a particle dropping procedure where you take a reduced word, S sub I, it drops as a particle between spots I and I plus 1, and you sort of build a tree by dropping the simple transpositions. Very much like Vienna's theory of heaps, you just want to build a tree. And then you can decompose the set of reduced words into words that give a fixed tree. And somehow that contribution gets encoded by this particular forest polynomial. So yeah, you can do an insertion procedure to get the forest polynomial expansion, which is an alternative way to compute these Schubert LR coefficients. And then there's a third way where you look at certain lattice points inside the Gelfand-Zetlin polytope determined from this forest. And inside that Gelfand-Zetlin polytope, there are certain lattice points whose, if you read them, they form a reduced word of an appropriate permutation. And you count those, and that's also an alternative description. So there's several ways to come at this answer, depending on where you start from.